this Liouville action, which I'll flash up quickly here. I guess we saw this in the last talk, and so yeah, in the last sort of 10 years or so, there's been a lot of work constructing this path integral by Kupiainen, Rhodes, Vargas, and others. But as I say, I'm not really going to talk about it. I'm going to more talk about this this probabilistic side in this metric measure space. But to that end, I should probably at least briefly introduce the properties of the Gaussian free field that I'm going to want to use later. So it's so I'm thinking of it as a standard Gaussian with respect to the directly inner product, which since we're in 2 dimensions, this inner product is conformally invariant. So we're going to get a conformally invariant log correlated field, one that only exists as a distribution, of course, because it's log correlated. So you have this blow up on the diagonal. Yeah, I should perhaps give this definition of the field. So this is going to be a zero boundary Gaussian free field on I'll say a proper domain in the plane. So what I do is I just take an eigenbasis of the smooth compactly supported functions in this domain with respect to this inner product, and my expansion in this basis is just going to be given by IID standard Gaussian variables, and okay, I mean it's hopefully pretty clear that this isn't going to converge pointwise, but it is going to converge almost surely in the space of distributions and in any negative Sobolev space. Okay, if I replace this proper domain with a whole plane, I can do the same thing, except I have to deal with a zero mode sort of. So I'm going to say that I replace this space with just the space of functions with zero mean, and then this GFF is a distribution modulo additive constant. So the inner product of H with a constant, I guess, is not defined. So yeah, so some properties that I'm going to want to use. Well, okay, so firstly, I want to argue that the law of this, I want to say that the law of this is independent of the choice of basis, and also from this, hopefully it's plausible that we have some version of the Gasanov theorem. So if I add to the field a function that's in this space HS0, then all I'm doing is shifting these coefficients alpha n by fixed amounts, and so the resulting field H plus F is going to be mutually absolutely continuous with what I started with. And okay, from this one can write down the Rodin-Nikodym derivative, which I don't think I'm going to need to do, but okay, perhaps I should also talk about the Markov property for the Gaussian free field. So the idea of this is that I take a subdomain and I look at the field outside the subdomain, and so what's the conditional law of the part I haven't seen, the field restricted to the subdomain, and so the answer is it's made up of the sum of two parts. So there's the part you can see, the part that's measurable with respect to what you've already seen. So this is the harmonic extension of the boundary values. And to that, you add an independent zero boundary field on your domain. Yeah, this gives you the remaining bit of the field. So one can think of this as akin to if you have a Brownian motion and you observe a Brownian motion outside of some time interval, what's the conditional law of the Brownian motion on this interval? Well, you know where the endpoints are. And so it's a Brownian bridge between those two endpoints. So in other words, so that's the same thing as taking an ordinary Brownian bridge that starts and ends at 0, and then adding the line segment that connects your two endpoints, which is the one-dimensional version of this harmonic extension. Okay, so yeah, so the fact that we've chosen this directly in a product means that we get sort of the exact analog of the Brownian motion in two time dimensions somehow. So yes, that should be enough about the Gaussian free field, I think. So now I suppose I should introduce the Liouville quantum gravity metric. So again, the motivation, the sort of informal idea that I have to put in scare quotes is that I have a random Riemannian metric, and the metric tensor is given by the exponential of some constant gamma multiplied by the Gaussian free field H. Okay, which, as we've said, this isn't defined pointwise. We're going to need to do some regularization to make sense of this. So this was done by these people, Ding, Duvida, Dunlap, and Falconet, and Gwen and Miller. So what you do is you look at some kind of mollification of the field, and then you construct the first passage percolation metric with respect to this mollification. So in other words, the length of a path is going to be given by the integral of e to the gamma times nice version of h along the path, and so this gives you a sensible metric. And then the idea is that if you send the scale of the mollification to 0 and you rescale these metrics in the appropriate way, you can take a subsequential limit of these metrics, and you get some random object that you can characterize by some axioms, which means that it turns out that it didn't matter sort of exactly how you mollified. So what are these properties? So your limiting object, which I'm calling d sub h, this is the LQG metric. So I'm claiming that you get a geodesic metric. So there is a geodesic between any pair of points. You get the Euclidean topology. The metric is local for the field. And what I mean by that is that if I want to know about just the length of paths that stay within some subdomain, I only need to see the field in that subdomain. Okay. And also, I have this Weyl scaling. So if I add a function to the field, then what I should get if I measure the distance between 2 points with respect to this new field, it should be given by just integrating this factor, which corresponds to exponentiating the function which I added. along a path. So okay, so in other words, I have this path, and when I add a function to the field, I just integrate the exponential of this function along the path, which I'm parameterizing by unit speed with respect to the original field, and then I get this. So this is sort of the natural way that the length of a path should vary when I add a function to the field. Apart from that, okay, instead of having gamma over 2 in front of the f, which is perhaps what you expect, I have to put gamma over the dimension of the metric, which is not going to be 2. It's going to be strictly bigger than 2, and it depends on gamma in some mysterious way. All right. So, okay, perhaps we cook up this d gamma from the first passage percolation approximations, but sort of after the fact, it turns out that this d gamma is the Hausdorff dimension of our LQG metric. In fact, it's the Minkowski dimension of our LQG metric, so it's slightly stronger. Okay, but this, let's see. So essentially, these properties turn out to characterize the LQG metric. Okay. So yes, I also want to talk about how the LQG metric will change under applying a conformal map to the parameterizing domain. So yes, so here I've written this coordinate change formula, which why do I need to do this? Well, the GFF is conformally invariant, but the LQG metric and the LQG area measure should not be conformally invariant because okay, the conformal map deforms the underlying space, right? So when I think about this as a Riemannian metric, you know, I have this exponential of the GFF with respect to, and I multiply that by Lebesgue measure somehow. Well, Lebesgue measure is being deformed, and the field is conformally invariant. So in order to get the same LQG metric that I had before, I'm going to need to add something to the field to account for the distortion of this conformal map. Okay, and this is the formula. So this 2 over gamma is just what you'd get if you had a smooth field instead of the GFF, right? So when I do e to the gamma times this, I'm going to get so the derivative of phi inverse squared, which is exactly what's compensating for, I guess, the change in Euclidean area that phi is applying. So there's also this gamma over 2, which is easier. It's easier to see where this comes from if I think about the area measure rather than the metric. So I'm going to so I need to briefly introduce that, I think. So okay, so if I do some regularized version of e to the gamma times h times Lebesgue measure, and I take a limit of these somehow, then I should get a random measure on my domain. And okay, so this was done first. This was Duplantier and Sheffield. And so this was done before the metric. I mean, we now know that this area measure is in fact obtainable from the metric as a Minkowski content. So this is work of Gwyn and Sung. So specifically, if I regularize the field at scale epsilon, then I have to multiply by epsilon to the gamma squared over 2 to get a scaling limit for these measures. And the gamma squared over 2 is where this gamma over 2 comes from. Okay, so so this coordinate change formula is slightly weird because of this extra term in the regularization. But the point is, it's okay. It is just a formula that one can write down, and this once one adds this factor, then if you do a conformal map to your domain with this coordinate change, this preserves the LQG area measure and it preserves the metric. Okay, so what this means is, so actually we have a little bit more structure than just a random metric measure space, because we have this conformal structure somehow, right? So we can think of what are called quantum surfaces. So this is an equivalence class of let's say a domain and the LQG metric and area measure on that domain, up to reparametrizing by conformal maps and doing this coordinate change. Okay, so in fact, these surfaces have some kind of conformal structure. So we don't have a single canonical embedding into the plane. We have a whole family of them related by conformal maps, but okay. So I'm thinking of these as these random surfaces. They're rough, but they have this kind of conformal structure. Okay. So yeah, so maybe let's now say why these are interesting to probabilists. So the idea is that we should be these surfaces should arise as scaling limits of random planar maps. So I don't know whether I need to say this to this audience, but a planar map is a planar graph equipped with an embedding into the plane. So I'm specifying how you embed it, at least up to homeomorphism. And okay, so if I pick a uniform random planar map, then the idea is that it should converge in the scaling limit to LQG with this special value of gamma, which is square root 8/3. So yes, and since I want to look at this on the level of the metric, this result of Le Gall and Miamont independently is maybe the best one to look at. So you take a uniform random quadrangulation. So this is a map where all the faces have degree 4, and you look at you just look at the graph distance in this map, and it turns out to converge in the scaling limit to okay, the square root 8/3 LQG metric, which is which is not, I guess, how they stated it at the time. So it converges in the scaling limit to, okay, the Brownian map. So this is an entirely different construction of what turns out to be the same notion of random surface, the same metric measure space. But yeah, so it's I guess later work of Miller and Sheffield that showed that these Brownian surfaces that are sort of constructed much more explicitly in terms of Brownian motion turn out to be equivalent to gamma LQG surfaces for the special value of gamma equals square root 8/3. So we don't have such construction when gamma does not equal square root 8/3. So this is sort of the special value that corresponds to uniform random planar maps. It corresponds to, I guess, central charge 0, if that physics language is nicer. But okay, so this is, but this is perhaps, one of the big results about random planar maps converging to LQG. So here's another one that okay, so I guess this works for other values of gamma. So so here I'm doing another construction based on Brownian motion. So I take two of these Brownian excursions with covariance that depends on gamma in some way that that I'm not going to remember. It involves a cosine. And I look at the continuum random trees generated from these Brownian motions. So what that means is I identify 2 points on these Brownian trajectories if I can connect them by line segments that stay under for the bottom one or over for the top one. Okay, and then I get these sort of fractal trees. And then I also glue these vertical segments together. And somehow these two trees mate together to form a sphere. Okay, I maybe don't have time to explain why this happens, but in the continuum, I get this mating of trees. I can discretize this by just I'm just going to look at vertical strips. So that's these numbered things, and then I get this random planar map where so I have edges. These red edges correspond to vertical strips being adjacent to each other, and then I have these green edges which correspond to strips being adjacent according to these segments that stay on one side of the Brownian excursions. Okay, so this is a discretized version of the mating of trees construction, which, as I said, by tuning the covariance of these Brownian motions, I can get different behavior. So again, the special value gamma equals square root 8/3, that corresponds to these Brownian motions having 0 covariance. Okay, so this is a random planar map model that again turns out to converge to LQG gamma. The reason this is the reason I'm bringing this up is that so here for these maps, we actually know a result about sort of a discrete conformal embedding of these maps converging to the conformal embedding of an LQG surface into Euclidean space. So okay, for a mated CRT map such as this with boundary, how do you discretely conformally embed it into the plane? Well, what you can do is first you need to embed the boundary onto the unit circle, and you're going to do this in order to make the distribution of the point at which you hit the boundary, the point at which a simple random walk hits the boundary, approximate the uniform measure on the unit circle. So this gives you a way to decide where the boundary vertices are going, and then once you've embedded the boundary vertices, you can embed the interior vertices harmonically. So yeah, so by that I mean each interior vertex is going to go to the center of mass of its neighbors. Okay, and this is given where the boundary vertices go, there's going to be a unique solution to this problem. So this is called the Tut embedding, and so intuitively this is like a discrete conformal embedding, and it turns out that under this embedding, you look at the uniform measure on the vertices, and you take the scaling limit, and well, I say scaling limit, I guess you're already embedding into the disk, so you're not really doing any further scaling, but the limit of the uniform measure on vertices as I increase the number of vertices in this map is the LQG area. Okay, so this is a result of Gwynn, Miller, and Sheffield. So in other words, so this scaling limit result is interesting to us here because what they've done is they've obtained the embedding of the LQG surface into the disk as a limit of these discrete conformal embeddings. Okay, so the question we want to address is, can this be seen at the level of the LQG metric? Right, so if I look at, let's say, the identity map from the LQG metric to the Euclidean metric, is this somehow a conformal embedding for some sense of the word conformal, which I need to define just in terms of the metric? Okay, so one attempt to like form this analog of conformality with just recourse to the metrics is I can ask whether this map is quasisymmetric. Okay, so here's the definition of quasisymmetric, and so for a map to be quasisymmetric, what I'm saying is what I'm insisting on is that there's some function that allows me to bound the ratio of the distances between the ratios of distances between 3 points in the image space, just in terms of the ratio in the original space. Okay, and okay, and so what I've written here is an upper bound, but of course, if I swap y and z, I can get a lower bound as well. So what this is saying is, I guess, this map doesn't distort triangles too much, let's say. Okay, so the ratio between the side lengths of a triangle in the image space is going to be controlled by the ratio in the original space. Okay, and right, so what has this to do with conformal maps? Well, if I'm just looking at maps between subsets of Euclidean spaces, then being quasisymmetric is equivalent to being quasi-conformal. So yeah, so we should perhaps quickly say what quasi-conformal maps are. So these are maps in which intuitively infinitesimal circles map to infinitesimal ellipses where the eccentricity is bounded. So a circle can't get distorted too much. And okay, hopefully it's intuitive that a circle not getting distorted too much is the same thing somehow as a triangle not getting distorted too much. Okay, but I'm working with these quasi-symmetric maps, I guess, just because you need less structure to define them. You just need a metric in order for this thing to make sense. Okay, but this is maybe capturing, okay, not conformality, but quasi-conformality. All right. So the question now becomes, okay, if I map from the LQG metric to the Euclidean metric, is this quasi-symmetric? Or in fact, maybe I take a different map here, but is that different map going to be quasi-symmetric? So as with many things about LQG, first this was done in the special case, in the square root 8/3 case. Okay, so this is the Brownian case. So this was done by Sasha Troscheit. So turns out that if you take the square root 8/3 LQG metric, not only is the canonical or canonical up to conformal equivalence embedding into the plane quasi-symmetric. In fact, there's no hope of embedding it quasi-symmetrically into Rn for any n. And so what's the idea of this? Well, well, this isn't quite how he wrote it, but the idea is that you can find some constant k such that I can find arbitrarily many points such that the maximal distance between two of them is at most k times the minimal distance. Okay, so if this holds for a fixed k and for every n, then that tells you that the space looks quite a bit different from Euclidean space, right? I mean, so this property is equivalent, in fact, to not being a doubling space. So a metric space is doubling if there's some constant m called the doubling constant, such that any metric ball can be covered by m balls of half the radius. Okay, so this is definitely true. This is definitely true for a Euclidean space, right? So in Rn, you can certainly cover any ball by let's say 4 to the n balls of half the radius, right? I mean, it should be 2 to the n, but maybe there's some okay, maybe some kind of awkward error happens if I try and take 2 to the n, but 4 to the n should definitely work, right? Okay, so you can also think of this as so there's in fact a notion of dimension that quantifies this. So not being doubling is equivalent to having infinite Aswad dimension, and so the Aswad dimension is somehow defined as the exponent that you need to take to cover a ball by balls of smaller radius. So in other words, okay, I have a ball of radius big R and I want to cover it by balls of radius small r, and so so in n-dimensional space, it should be r over r to the n should be the number of balls I have to take, right? And so that exponent essentially is the Aswad dimension. So you can think of this as sort of a very local version of the Minkowski dimension. So it's sort of what's the Minkowski dimension of somehow the thickest bit of your space, right? So somehow these LQG surfaces, even though they have finite Minkowski dimension, there are somehow these small places where you have this sort of behavior that couldn't possibly happen in a finite dimensional space. Right. So and the point is that being doubling or equivalently having finite Aswad dimension, these things are preserved by quasisymmetries. So if right, so because this space isn't doubling, because this space has these cliques, any quasi-symmetric image is also going to be not doubling. So somehow, maybe this is easiest to see using the cliques somehow. So if I apply a quasi-symmetric map to this inequality, somehow the constant k is going to change, but it's going to change by something that's just given by the psi from the quasi-symmetry. So some version of this inequality is still going to hold. You're still going to have these cliques in the quasi-symmetric image. All right. So yeah. So this property is telling you that you can't. Well, I mean, you can't embed quasi-symmetrically into any space, into any doubling space. So in particular, not into Rn, not into the sphere, not into any finite dimensional Riemannian manifold, in fact. Okay, and so this so in Troscheit's paper, these cliques are found using the Brownian motion. Okay, so this only works for gamma equals square root 8/3. But we have to do something different in order to generalize this to other values of gamma. And so, yeah, I suppose I've got time to say what the idea is. I'm not sure how well this picture is being rendered over Zoom, but okay, we'll see. So the idea is, so I want to find endpoints such that the pairwise distances between the points are all comparable. Okay, so what I'm going to do is I'm going to draw this star with endpoints. So here n is 4, and so the idea is I'm going to add bump functions to the field in order to make geodesics between any of these 2 points, any pair of these points, sort of stay within this star. Okay, so I do this by maybe just adding a massive bump function to the field that makes geodesics not want to leave the star. I also need to make sure that so maybe within one of these annuli, I'm going to add a not as big bump function to make sure that all these geodesics accumulate roughly similar amounts of distance crossing one of these annuli. Okay, so in other words, by sort of adding some function to the field, I'm going to make it very likely that any geodesic between any pair of these points sort of has to cross this annulus twice, and that's going to be where the geodesic accumulates more or less all of its length. Okay, and then I just adjust these points by sort of moving them along the path so that all the distances become roughly equal. So that's sort of the idea. So what I've done is I've argued that if you add some function to the field, then it's very likely that I can find these endpoints that are approximately the same distance. When I added this bump function by this sort of version of Gasanov for the GFF, what I got was mutually absolutely continuous with respect to the law of the original field. And so with positive probability, I can find these endpoints with respect to the metric given by the original field. Okay, so this gives me what I want with positive probability, but I need it almost surely, and so all I do for this is use near independence for the field in sort of different places. So I'm saying across annuli, and these annuli, the annuli in this bullet point are not the annuli in the picture. So let's maybe ignore that. What I'm saying is the field is sort of nearly independent in different places because of this Markov property, right? So I can look for this clique in sort of one region, and then the field in another region conditionally on that is sort of nearly independent of it by the Markov property of the Gaussian free field. So if I do some appropriate exploration of the field, then I'm going to find this clique somewhere, almost surely. Okay. So right. So that's broadly the idea of this result. So yeah, I guess yeah, this is a somewhat negative result. You know, the sort of conformal structure on this LQG metric turns out to not really be conformal at the level of the metric itself, which is slightly odd. Yeah, so I will point out that in a way, these are sort of soft arguments that don't use I've sort of just used properties of the Gaussian free field here, right? I haven't said much about the metric itself. So it feels like there should be a more general result somehow, like if you have any sort of stochastically self-similar metric space with enough randomness, then you should get this this type of behavior somehow. Again, you know, what is this more general result? I'm not sure, but this is something I'd like to think about. Yeah, another thing is, yeah, maybe maybe this notion of quasisymmetry wasn't the right one. So I guess it's the one corresponding to this Aswad dimension, which is kind of the strictest. It's the largest somehow sensible notion of dimension you can put on a metric space. So maybe these LQG surfaces, they had infinite Aswad dimension, but they have finite Minkowski dimension. So maybe maybe there's a better analog of conformality that's sort of more to do with the Minkowski dimension or some other notion of dimension, under which we do somehow see some of the conformal structure in the metric. Okay, and of course another thing you could ask is, what about infinite dimensional spaces? If you look at an infinite dimensional space, I mean, these behave differently. You know, these aren't doubling anymore, so these cliques aren't a problem. So maybe maybe the LQG metric embeds really nicely into, you know, Hilbert space or something. This isn't really studied yet. And one could try and, you know, embed random planar maps into an infinite dimensional space in a way that's somehow tight, and maybe try and obtain a sort of scaling limit for this. I don't think this has much been studied. I mean, there are certainly results about embeddings of general planar graphs into infinite dimensional spaces. Well, these are sort of worst case results, right? I don't think it's really known. You know, if you take a random planar map, you know, what's the lowest distortion you can get for an embedding into L2 or LP? So this will be an interesting avenue, I think. But yeah, I mean, that's more or less everything I wanted to say. I guess I mostly wanted to start thinking about this stuff again and maybe advertise some of these future directions. You know, so yeah, hopefully at least this last slide is maybe sparking some imagination. But yeah, thanks again for inviting me. And yeah, I'll take any questions.
Thank you very much, Liam. Questions from the audience?
Thanks. Yes, I have maybe a naive question. So if you take a random planar map, maybe a mated sqrt map, so does your result implies that if you take an embedding in RD, let's say, then the Aswad dimension, it goes to infinity when you let the size of the map goes to infinity?
Yeah, that's so let's see. So I guess so right. So we have I guess for some kinds of random planar map, we know like scaling limit of the graph distance, right? So yeah, so you'd want to try and deduce that the Aswad dimension goes to infinity from that, right? Which I sort of don't want to. I don't want to say. I'm sort of worried that there might be some kind of exchange of limits that's difficult to do here, because I guess you don't. Yeah, I guess these sort of cliques, these sort of sets of points, you don't really have.
Oh, okay.
You're not really seeing the points when you go to the limit, but maybe. Yeah, I can't tell. I mean, maybe that's maybe there's an interesting story there.
Or maybe if you measure something else, then yeah, that's what dimension.
Yeah. Okay. Yeah. Again, the Aswad dimension is sort of weird because it's sort of so local somehow. You just need some tiny part of the space to break it, to sort of send it to infinity. And yeah, of course. So like, well, okay, I guess, I mean, the reason somehow like the way we cook up this mysterious D gamma that is the Hausdorff-Minkowski dimension is by looking at the it's sort of constructed originally as like an exponent corresponding to distances in planar maps that approximate the. So with something like that, you can sort of get the dimension from the discrete.
Yes.
Yeah. So maybe, yeah. But maybe Aswad is sort of different because it's so local. I'm not actually sure. I don't know. But yeah, thanks for the question.
Okay, any more questions? Okay, if not, let's thank Liam and Lorenzo again. Thank you very much. Okay.
All right, great. Thanks very much.
Thank you.